So far, we have discussed the gradient, which takes a scalar field and produces a vector field, and we have discussed the divergence operator, which takes a vector field and produces a scalar field. Now we introduce the curl operator. The curl operator takes a vector field and produces another vector field. And what's very special about the curl operator is that its definition, the one that we provide here, only makes sense in 3 dimensions. So now we will only talk about the differential operator that takes a 3-dimensional vector field and produces another 3-dimensional vector field. So the curl operator is only defined in 3 dimensions. And let me remark at this point that it is also known as a rotation operator. So the curl takes a vector field and it produces another vector field, another 3-dimensional vector field. F is a vector field in 3 dimensions, and so is the curl. If we write down the curl in its 3 components, it looks as follows. We take a vector field with components f1, f2, and f3. This is mapped to the following new vector field, again with 3 components. We take del2 of f3 minus del3 of f2. That's the first component of the curl. Then we take negative del1 of f3 plus del3 of f1. That's the second component of the curl. And the third component of the curl is given as follows. We take del1 of f2 minus del2 of f1. As you can already tell, this special formula looks a bit more complicated than what we have seen with the gradient or the divergence operator. There are lots of indices and signs here. At this point, let's not get into the mathematical background for that. The mathematical background for that will be explored shortly. But as for now, perhaps if you take a look at this formula, maybe you recognize some patterns here, so it actually becomes easier to memorize. That being said, one thing to memorize for sure is that the curl of a 3D vector field is a 3-dimensional vector field. The curl of a 3D vector field is again a 3D vector field. Before we approach the mathematics and physics of the curl operator on 3-dimensional vector fields, let's just do one formula calculation. Just one example. I take a vector field in 3 dimensions, and it has the following 3 components. The first component is x1 times x3 square. The second component is the exponential of x1 times the sine of x3. And the last component is just the product of x1, x2, and x3. That gives me the 3 components. So let's compute the curl of this vector field. We begin, of course, by writing down the definition. And now it's just some standard calculations. We easily see the first component is x1 times x3 del 2 of f3, and then we subtract exponential of x1 times the cosine of x3. That is the first component of the curl. The second component is also very easy to calculate. It's just negative x2 times x3 plus 2 x1 x2 second component, and the last component exponential of x1 times sine of x3, and then this component here does not depend on the second variable, so it's just 0. And that altogether completes the example.